All right, let's crack open the world of electricity and take a deep dive into the difference between AC and DC.
Alternating current and direct current, that is.
You got it. And get this. By the time we're done with this deep dive,
You'll be able to spot them.
just by looking at,
Yeah, like an oscilloscope reading.
or some data logging output,
Exactly.
no fancy gadgets needed, just a good understanding of how electricity works.
It's going to be like having X-ray vision, but for circuits.
I love that analogy.
We'll break it down, start with the basics, and then work our way up to those telltale signs that scream AC or DC.
Sounds good to me. So let's start with the fundamentals. What are those tiny particles that make electricity happen? Those electrical charge carriers?
Okay, so we got to start with atoms, right?
Of course.
But not the whole atom, just those tiny little electrons zipping around the nucleus.
Ah, those negatively charged particles.
Yep, there are stars. Because they're free to move around, they make electrical current possible.
Okay, so electrons on the move. That makes sense. But what exactly is electrical current then?
Okay, imagine water flowing through a pipe. Yeah.
Okay, I'm picturing it.
So electrical current is kind of like that. It's the flow of those charged particles, those electrons, through a conductor, like a wire.
So the wire is like the pipe.
Exactly. And just like how we measure the amount of water flowing through a pipe in, say, gallons per minute, we measure the amount of charge flowing per second in amperes, or amps for short.
So more amps, more electrons flowing. Got it.
Now, we need to talk about the two main types of current:
Okay, hit me with them.
direct current, or DC, and alternating current, or AC.
All right, let's start with DC. What's the story with direct current?
So with DC, the electrons flow steadily in one direction. It's like a one-way street for those little guys.
Okay, I see.
A perfect example of that is a battery.
Makes sense. That's why batteries have a plus and a minus sign, right? To show the direction of the flow.
Exactly. And if you were to look at a DC signal on an oscilloscope, you'd see a flat line.
Oh, interesting.
It might be above or below the center line, but the point is, it's straight. That tells you the current is constant and flowing in just one direction.
Okay, so DC is all about consistency. Now, what about AC? What makes it so different?
All right, so picture a dance floor, right?
Okay, I'm picturing it.
With AC, the electrons are constantly switching directions back and forth, kind of like they're dancing to the beat.
Oh, so instead of a steady flow like DC with AC, the electrons are doing the electric slide.
Something like that.
Yeah.
And the beat of the music in this case is the frequency of the alternating current.
Interesting. So that back and forth movement is what we have in our homes, the electricity from the outlets.
You got it. That's AC.
So if I hooked up my oscilloscope to an outlet, what would I see? It wouldn't be a straight line like with DC, right?
Nope, you'd see a wave. It's constantly crossing that center line as the direction of the current changes.
Ah, okay. That makes sense. So DC is a straight line and AC is a wave. That's a pretty clear visual difference.
Yeah, exactly. And that's the key to identifying them from oscilloscope traces or those data logging graphs. Just by looking at the shape, you know instantly if you're dealing with AC or DC.
That's so cool. You don't need a degree in electrical engineering to figure it out.
Not at all. It's like a secret code, you know? Once you know it, it unlocks a whole new understanding of the electrical world around you.
That's a great way to put it. So we've got those visual cues down. But let's dive a bit deeper into what makes these two types of current tick. What about those terms I hear sometimes, like frequency and peak value?
Okay, so those are really important, especially when we're talking about AC. Frequency, which is measured in hertz, tells us how many times that AC current changes direction every second.
That's just like how fast the electrons are switching directions.
Yeah. Think of it like how fast the beat is in that electron dance party we were talking about.
So a higher frequency means a faster dance party.
You got it. Now, the standard frequency for the AC in our homes is 50 hertz, meaning the current changes direction 100 times every second.
Wow, that is a fast beat. And what about that peak value thing? What does that tell us?
So the peak value is the highest point that wave reaches.
Okay.
It's like the maximum value of the current or voltage, whether it's going positive or negative.
So it's the most intense moment of the dance, the peak of the energy.
Yeah, exactly. So frequency tells us how often the current changes direction, and peak value tells us the maximum strength of that current or voltage.
Got it.
But here's where it gets a little more interesting. When we talk about the strength of AC, we usually use something called RMS value.
RMS value. I've heard that term, but I'm not sure what it means. Why not just stick with the peak value?
Well, the peak value only gives us a snapshot, like a single frame from a movie. RMS, which stands for root mean square, gives us a more accurate measure of the average power delivered over time.
Ah,
So
okay.
it's like taking the entire dance routine into account, not just the most energetic move.
That makes sense. So RMS is important because it lets us compare the power output of AC to DC.
Exactly. It tells us what DC voltage would create the same amount of heat in a resistor.
So when we talk about our household electricity being, say, 120 volts, that's the RMS value, not the peak value.
You got it. The peak value is actually higher, but the RMS value is a more practical way to measure and compare the power of AC sources.
This is making me think about all the different ways we use electricity. It's not just lights and appliances, is it?
Oh, definitely not. Both AC and DC have their own strengths and are used for all sorts of applications, from powering our homes to running complex electronic devices.
It really is incredible. I'm starting to see the world of electricity in a whole new light.
That's what we like to hear. The more you understand these basic concepts, the more you can appreciate the ingenuity behind all the electrical systems that make our world work.
Absolutely. And speaking of those systems, let's talk about why we use both AC and DC. What are the advantages and disadvantages of each?
All right, so let's get into that.
Okay, so let's get into that. Why do we use both AC and DC?
Well, it all comes down to efficiency and practicality.
Okay, I'm intrigued. Tell me more.
So one of the big advantages of AC is that it's pretty easy to change its voltage.
Okay.
And that's super important for transmitting power over long distances. You see, when electricity travels over those long power lines,
Yeah.
a lot of energy gets lost along the way.
Ah, because of resistance.
Exactly. It's kind of like friction working against the flow of electricity. To keep those losses down, we need to transmit electricity at really high voltages.
Okay.
And AC makes it simple to step up the voltage for transmission and then step it back down for us to use safely in our homes.
I see. That's why we have those big transformers, right?
Yeah, you see them on power poles and in substations.
Right.
They're basically changing the voltage of that AC current.
Got it. So AC is great for long distance travel. What about DC? Where does it fit in?
Well, DC has its own perks.
Okay.
It's super efficient when it comes to powering electronics, especially those with delicate parts like, microchips.
So that's why we use batteries, which are DC, for things like smartphones and laptops.
Exactly. DC delivers a nice steady flow of energy,
Oh, okay.
which is perfect for those sensitive circuits.
This reminds me of something I read about. Wasn't there like a big rivalry between Thomas Edison, who was all about DC, and Nikola Tesla, who pushed for AC?
Ah, you're talking about the War of Currents.
Yeah, that's it.
It was a fascinating time back in the late 1800s when these two brilliant inventors were battling it out.
Wow. So who won?
Well, I mean, if you look at the power grid today,
Yeah,
it's pretty clear that AC came out on top.
right.
But DC is still super important, especially in the world of electronics.
Ah, so it wasn't a complete knockout, more like each had its own strengths.
Exactly. And that's what makes the history of electricity so interesting. It's all about innovation and, technology evolving.
Speaking of innovation, let's circle back to those oscilloscope readings for a second. We know that a straight line means DC and a wave means AC.
hmm
But what if we see something, well, a little more funky? Like, what if the line isn't perfectly straight or the wave isn't perfectly smooth?
Okay, so that's where things get really interesting.
I knew it.
Those little imperfections, those bumps and wiggles, can tell us a lot about what's going on in the circuit.
Really? Like what?
Well, let's say you're looking at a DC signal, and instead of a perfectly flat line, you see some little ripples.
Okay.
Those ripples could mean there's some noise or interference happening in the circuit.
So it's like those little imperfections are clues to problems or variations in the current.
Exactly. And the same goes for AC. If the wave isn't perfectly smooth, it could indicate distortion or harmonics in the signal.
So even those tiny deviations from the ideal shape can tell us a lot about what's going on with the electricity.
Absolutely. It's all about learning to read those subtle signs and figuring out what they're trying to tell us.
This reminds me of something else we talked about. Different charge carriers.
Yeah.
We were talking about electrons mostly, but aren't there other types of charge carriers out there?
You're right.
Yeah.
While electrons are the usual suspects in electrical circuits, there are other particles that can carry an electrical charge too, and they play important roles in certain materials and applications.
Like those holes you mentioned earlier, right? The ones in
Well,
semiconductors.
That's right. Semiconductors are those special materials that are used to make things like transistors and microchips.
Yep.
And in these materials, we can have these holes that act like positive charge carriers.
So it's like a missing electron creates a positive charge.
Yeah. It's a bit mind-boggling, I know.
It is.
But it's key to understanding how semiconductors work.
So it's like a whole different dance party happening in those semiconductors.
You could say that. And understanding how these different charge carriers behave is super important for developing all those fancy electronic gadgets we use.
This just goes to show that electricity is full of surprises. There's always something new to learn.
Absolutely. And that's what makes it such an exciting field to explore.
It really is. And speaking of exciting fields, let's shift gears and talk about circuits.
Yes, circuits.
They're like the roads of the electrical world, right?
Yeah.
Guiding all those electrons to where they need to go. But how do they actually work?
Okay, so think of it like a racetrack. For electrons, you need a starting line, a track to follow, and a finish line.
So in a circuit, the starting line would be the power source, like a battery, right?
Right.
And the finish line is back at the power source, making a complete loop.
Exactly. And the track itself, that's the wiring, the conductors that connect all the different parts of the circuit.
Okay, so those components, things like resistors and capacitors, those are like the obstacles on the racetrack.
I like that. Each component has a specific job to do. They control or change how the electricity flows. For example, resistors are like speed bumps.
Okay.
They resist the flow of current, slowing those electrons down.
Ah, that's why they're called resistors. They literally resist the current.
Exactly. And we measure how much they resist in ohms.
Okay, so resistors control the flow. What about capacitors? What's their role in all of this?
Capacitors are like little energy storage tanks along the racetrack.
Oh, okay. They can store up electrical energy and then release it later when it's needed.
So they're like tiny little batteries within the circuit.
You could say that. And they come in handy for smoothing out those voltage fluctuations or providing a quick burst of energy.
Gotcha. So resistors control the flow, capacitors store energy. What other key players are there in this circuit game?
Well, there are quite a few.
Mm-hmm.
But one of the most important is the transistor.
Okay, tell me about transistors.
Transistors are like the traffic cops of the circuit. They can switch the current on or off,
Wow.
or even amplify the signal.
So they decide where the electrons go.
You could say that. Transistors are really what make it possible to build all those complex electronic circuits that do so many amazing things.
It's incredible how it all works together to make these intricate electrical pathways.
It really is like a perfectly coordinated dance, you know? Each component playing its part, making sure the energy flows smoothly.
Now, I've seen those diagrams with all the lines and symbols, those circuit diagrams, right?
Yeah, exactly. But honestly, I've never really understood how to read them. What's the deal with those?
So those circuit diagrams, they're like blueprints for electrical engineers.
I see.
They use standard symbols to represent each component and how they're all connected.
So it's like a special language for describing electrical circuits.
Exactly. Once you learn the symbols, you can read a circuit diagram and understand how that circuit works.
That's pretty cool, like cracking a secret code.
And those diagrams, they're crucial for designing, building, and fixing any kind of electrical system.
This has been so enlightening. But before we wrap things up, I think it's super important to talk about safety when dealing with electricity.
Absolutely. Safety should always come first.
For sure. So what are some key things to keep in mind?
All right, so always use insulated tools and equipment. That's rule number 1.
Got it.
And never, ever work on a circuit that's live.
Right, makes sense.
And before you even think about tinkering with anything electrical, make sure you understand how the system works.
Those are all great points. It's definitely better to be safe than sorry when it comes to electricity.
Couldn't agree more. Electricity is powerful stuff. Always treat it with respect.
We've covered a lot of ground in this deep dive, from those tiny particles of electricity to the intricate world of circuits.
It's been quite a journey. I think it shows just how fascinating and complex the world of electricity really is.
And the coolest part is, there's always more to learn, more to explore and discover.
Absolutely. So stay curious, keep asking those questions, and never stop learning.
Great advice. And that wraps up our deep dive into the world of electricity. Until next time, stay charged up and keep exploring all those amazing scientific wonders out there.